Hello and welcome, students. In last lecture, we had started with the topic circles, and I taught you the basics of this topic, in which we also learned certain theorems. So quickly, I will tell you what we did in the last lecture. So I just taught you, I had given you the idea about the circumference of the circle. See, this is circumference of the circle. This is the circumference of the circle. Then this is center of the circle, this point, from which all the points are equidistant. Then distance between the center and any one point on the circle is the radius of the circle. If you have any 2 points on the circle and you join them with a straight line, then you call it as a chord of the circle. If you have 2 points on the circle, you are joining them, and the segment joining those 2 points, when passes through the center, then you get the longest chord of the circle, which is the diameter. And it is found the diameter of the circle is 2 times the radius of the circle. So this was the beginning that we had done. After that, I taught you about concentric circles. What are concentric circles? Equal circles. Circumscribed circle. Circumscribed circle is, say you have a polygon, and then you draw a circle in such a way that the points, the vertices of the polygon are lying on the circle. Then you call such a circle as a circumscribed circle, and it is circumscribing the polygon. Okay, here it is circumscribing the quadrilateral, and here the circle is circumscribing the pentagon. Then we have done the inscribed circle. In case of inscribed circle, we have a circle which is drawn inside a polygon, and this circle is touching all the sides of the polygon. You can check. Here it is touching all the sides of a triangle. Here it is touching the sides of a quadrilateral, and here it is touching sides of a pentagon. So these are all inscribed circles. Then I taught you about the chord. Chord we have already done. The diameter is the longest chord. And then we did a point where we learned that from the center of the circle, when you are joining the midpoint of a chord, then this line segment, which is bisecting the chord, is always perpendicular to the chord. Further, the converse of that is, if I draw from the center of a circle, if I draw a perpendicular on any chord, then that segment which is perpendicular to the chord will divide the chord into 2 equal parts, that is, it will bisect. Then we learned that when in a circle, if I have a chord which is longer, suppose I have 2 chords, say CD and AB, and it is found that AB chord is longer in length than CD. So longer the chord in a circle, nearer it is, closer it is to the center of the circle. Okay, so if you have a longer chord, it will be closer to the circle than a shorter chord in a circle. Okay, then we also learned that through 3 points in a plane which are not collinear, any 3 points which are not on one single line, they will always define a unique circle. Then the next point we did was, here we did the next point, that if 2 chords are equal in length, if 2 chords in a circle are equal in length, then they are equidistant from the center. And the converse of that will be, if 2 chords are equidistant from the center, they will automatically be equal in length. Then we did arc and types of arc. Okay, so a part of the circle is known as arc of a circle. And remember, the arc, if it is smaller than the semicircle, you call it as the minor arc, and the arc which is greater than the semicircle, you call it as the major arc. Then we learned about the segment. a part of the circle which has got the boundary as one chord and the arc. Okay, like here, see, AB is a chord. So you consider AB as one boundary, and this arc you consider as another boundary. So what it gets you, a segment. So this one is the bigger segment, okay, which is major segment. It is the major segment. So remember, a chord and the major arc will get the major segment. The chord and the minor arc will get you the minor segment, okay? So remember, for the idea about remembering the segment is that arc is actually the length. Remember, students, that when you talk about arc, you just talk about the length. So here, you know, when I'm saying the minor arc, I mean this, and you know, this is nothing but the part of the circle, okay? And it is not a closed figure. It is just it is just arc. It will have length. It will have length. But remember, when it comes to the segment, remember, the segment is not only length. Segment is the area. Now here you have, see, this is minor arc. This is minor arc, and what is it? This is the chord. So what do you get? You get a bounded figure, a closed figure. So remember, this is segment. Okay, so when you say a segment, remember, it's area. But when you say arc, it is simply the length. It is simply the length. I hope you followed it. Then the next we did was the relation between the arc and the segment. And for that, we had done theorem. See, the first theorem that I took in the last lecture was that we did that angle subtended by an arc at the center will be double the angle subtended by arc in the remaining part of the circle, in the remaining part. Now see, when you say arc APB, what is the remaining part of the circle? The remaining part of the circle is complete circle other than APB. So see, the remaining part of the circle will start from A, C, and B. Now, you have any angle subtended by APB anywhere in the remaining part of the circle, it will have the measure 1/2 times of AOB. See, this AOB angle, which is subtended at the center by the arc APB, it will be double of this angle. It will be, this angle at the center will be double of this angle. Okay, so this we did. And after that, we did the another theorem was, another theorem we did was the angle in the same segment are always equal. Now you can check, see, look at the arc APB, okay? Now this arc APB, if I join this point A with B, okay, I get a chord. If I join A with B, I get a chord AB, yes. Now what I do is, I get one segment. See, this is one segment, which is the minor segment. And then what is the major segment? The major segment you have is this. So this is major segment here. That is chord AB and the major arc. This is major segment. So now remember, students, that there can be infinite angles in this major segment. Those all angles are called angle in the same segment. That is what is written here. You can check. You can check here, it's written angles in the same segment of a circle are equal. Angles in the same segment of a circle are equal. You can check this. But that, so here, you know, this, you got angle at, see, you got angle here, this angle and this angle. They are angle in the same segment. I can have few more angles like that. See, I can have, see, this angle is also in the same segment. You can have infinite such angles. Remember that. See, these all angles are in the same segment. They all are equal. You could have even said that angles subtended by an arc, angles subtended by an arc in the remaining part of the circle are equal. You could have said even like that. So there are two statements you can say. You can say this statement that angles in the same segment of a circle are equal, or you could have said that angles subtended by an arc. See, this is APB, which is subtending angles at the remaining part of the circle, and they all are equal. These all angles are equal. You can check. See, they all are equal. You could have said even this. Now, next we have here is, see, the next theorem we did was, see, we did the angle in a semicircle. Okay, this we had not done. We have to start from here. So let us start from this theorem 7. We are starting from here. So what is this theorem? It says the angle in a semicircle is right angle. The angle in a semicircle is right angle. So students, you can check here that you have a angle in a semicircle is a right angle. See, you have a circle here. You have a circle here with the center at O. AB is the diameter of the circle. So above AB, what you have is a semicircle. And below AB, what you have is another semicircle. You check this. This is semicircle. This is what they mean by semicircle. So this is the semicircle they're talking about. This is semicircle. This is another semicircle. And this is AB, the diameter. Now what's happening here is, see, this AB diameter, this AB, the diameter, is subtending an angle at a point on the circle C. This point is C. What we notice is this angle ACB is being subtended by it is being subtended by the diameter AB on the circle or at a point on the circle. See, I could have had, see, I could have had here see, I decide another point on the circle and I join that point with point A and point B. Again, what I notice, say this point, I call it as a D. So now I can say that angle ADB is subtended. Angle ADB is subtended by diameter AB on the circle. It is subtended by diameter AB on the circle. See, I'm talking about this angle. Here it is, this angle. You can have infinite such angles. You can have infinite such angles. See, I can decide another point. Again, this and this. See, once again, this angle which I'm getting, say this point is E, this point is E. Again, this angle also is subtended by diameter AB on the circle. Now, when you say this, all angles are subtended by diameter AB on the circle. Now, what happens, you know, this diameter, it decides the semicircle. See, this diameter decides half of the circle, that is semicircle. So what you have is, above the diameter, you call this as a semicircle. So can I call these all angles as angles in semicircle? Definitely yes. I can call these all angles as angle in semicircle. And remember, these all angles are 90-degree in measure. These all are 90-degree. They all are 90-degree in measure. This is 90-degree. This is also 90-degree angle. This is 90-degree. And here this angle is also 90-degree. Remember that angle in a semicircle is always 90-degree. It's a right angle. When you say angle in a semicircle, how are you going to get a semicircle? A semicircle is half the circle. And when you say half the circle, the diameter will definitely come in picture, because diameter divides the circle in two halves. It is diameter which divides the circle in two halves. So you can say this in two ways. One is, you can say that angle in a semicircle is a right angle, or you can say the angle subtended by diameter at any point on the circle is a right angle. Angle subtended by diameter at any point on the circle. You can check. These all angles are subtended. See, I start with an arrow here. See, these all angles are subtended from A here and from B here. See, so this angle which you are getting, it is made by diameter. I hope you understood. So remember that angle subtended, angle in a semicircle is right angle. So you can write this statement. Please write this statement that angle in a semicircle is, you will please make a note of it. Angle in a semicircle is right angle, and draw this diagram and make this 90-degree here, 90-degree. Fine, you can do this. Now we move to next. See, the next is cyclic properties of circle. See here. Let us read this first. When a quadrilateral is inscribed in a circle, a quadrilateral is inscribed in a circle, that is, you have the circumscribed circle. That is, the vertices of quadrilateral lie on the circumference of a circle. The quadrilateral is called a cyclic quadrilateral. It is called a cyclic quadrilateral. See, I will show you an example. Suppose you have a circle. Okay. Now you draw a quadrilateral in such a way that vertices, you draw the quadrilateral in such a way that vertices of this quadrilateral are lying on the circumference of the circle. So if I name this quadrilateral as ABCD, if I name this quadrilateral as ABCD, then remember that this quadrilateral ABCD is a cyclic quadrilateral. It is a cyclic quadrilateral. The points which lie on the circumference of the same circle are called concyclic points. So now you can say, see, these points that you have here, these points, which points? I mean the point A, point B, point C, D. These points are known as concyclic points. They are concyclic points. Now we go for a theorem. See here. See, the theorem here is the opposite sides the opposite angles of a cyclic quadrilateral, what is that meaning? It means quadrilateral inscribed in a circle, the one which I had just drawn. A quadrilateral which you inscribe inside a circle. That is, all the vertices of the quadrilateral are lying on the circumference of the circle. Read it once again. Read it once again. See, the opposite angles of a cyclic quadrilateral are supplementary. When you say two angles being supplementary, what does that mean? It means that the sum of two angles is equal to 180 degrees. Okay. So here the theorem is the opposite angles of a cyclic quadrilateral are supplementary. So students, see here, you will write the statement. Please write the statement in your notebook. Make sure that you write it. Very important statement. You are going to have problems based on this. Now here I show you what does that mean. See, you have here a circle and a quadrilateral is inscribed in this circle. That is all the vertices. You can check the vertices of the quadrilateral A, B, C, D. What do you notice? That these vertices are lying on the circumference of the circle. So you call them as in cyclic quadrilateral. You call these points as concyclic points, and you call the quadrilateral as cyclic quadrilateral. Now what the statement mean here is, the statement was the opposite angles of a cyclic quadrilateral are supplementary. Now in this cyclic quadrilateral, let me highlight it. The cyclic quadrilateral I will highlight. See, this is the sides of the quadrilateral are AB, BC, AD, and CD. This is the cyclic quadrilateral. And what do we have? We have the angles, the opposite angles of a cyclic quadrilateral are supplementary. That is, see, the opposite angles in this quadrilateral ABCD. This angle, okay, and this angle. See, they are known as the opposite angles. These two angles are supplementary. That is, if I add the angle ADC plus angle ABC, you see this, I will get equal to 180 degrees. The another pair of opposite angles are this and this. If I add these two angles, that is angle BAD and angle BCD. Angle BAD, angle BAD, and angle BCD. Again, it is 180 degrees. It is 180 degrees. So the opposite angles of a cyclic quadrilateral are supplementary. You will make a note of that statement, as I said. Please make a note of this statement. Opposite angles of a cyclic quadrilateral are supplementary. You can draw the diagram and just make sure to understand what you are writing. This plus this equals to 180 degree. This plus this equals to 180 degree. You can write them too. Yeah, so here related to the same theorem about the cyclic quadrilateral, we have two more important statements. Let us read them and understand them too. See, here we have, if the opposite angles of a quadrilateral are supplementary, the quadrilateral is a cyclic quadrilateral. So basically this is converse of the above statement. I hope you understand the meaning of converse. In the above theorem, what you said that if If the quadrilateral is a cyclic quadrilateral, then the opposite angles of the quadrilateral are supplementary. And here what you are saying, here you are saying if the opposite angles of a quadrilateral are supplementary, then the quadrilateral is a cyclic quadrilateral. Okay. So suppose here I say, suppose I give you a quadrilateral. For example, suppose I give you a quadrilateral, right? Say I give you a quadrilateral here like this. And then I say that these two angles here, this angle and this angle, when added, they give me 180 degree. This is what I said. Now, what does that mean? It means that this quadrilateral is a cyclic quadrilateral. The sum of two angles is giving me 180 degree. It means the opposite angles, are, these two angles, opposite angles are supplementary. It means the quadrilateral will be a cyclic. That is, these vertices will lie on a circle. The vertices will lie on a circle. Okay, if I try, I can, okay, it is, see. Just try to understand. I know it is not coming well, but then this is what I mean. What? That these points will lie on a circle. These points will lie on a circle. Next, the next is here. See, angle of major segment is acute and angle of minor segment is obtuse. Okay, now see here, look at this. This quadrilateral ABCD is a cyclic quadrilateral. Yes, because the vertices A, B, C, D, they are lying on the circumference of the circle. Okay, let us name this center as O. Now, the two opposite angles, if you want to decide a pair of opposite angles, so let us decide this pair, the angle at B and angle at D. Now, if I ask you, what is if I decide these two angles, this pair of angles, then see this angle, that is ABC, and the other angle is ADC. They are both subtended, they are both made in two different segments. They are both lying in two different segments. That is, for that, you will have to join A with C to make a chord. Okay. Now, what I can say that angle ABC, it is lying in the major segment. Angle ABC is lying in major segment. You can check. See, this is major segment. The chord AC makes two segments. The chord AC with the major arc gets you the major segment. This is major segment. This one is a major segment, and this angle ABC is in the major segment. This angle ADC is in the minor segment. Look at the angle ADC, it is in the minor segment. Remember, in a cyclic quadrilateral, the angle which is in the major segment is acute angle. See, this angle is acute angle. The angle which is in the major segment is acute angle, and the angle which is in the minor segment is the obtuse angle. It is obtuse angle. That is what it is said. Angle in major segment is acute and angle in minor segment is obtuse. Further, in the adjoining figure, angle ABC is the angle of major segment, so it is acute. Angle ABC is less than 90 degree. You can check this is less than 90. In the same way, angle ADC, the one which I showed, is the angle of minor segment, so it is obtuse. That is, angle ADC is greater than 90 degree. You can write these 2 points also, very important points. We'll go ahead now. See. Now go for the next theorem. See, this next theorem is it says the exterior angle of a cyclic quadrilateral is equal to interior opposite angle. The exterior angle of a cyclic quadrilateral is equal to interior opposite angle. Now see, here you have a cyclic quadrilateral. This is, you got the vertices of the quadrilateral A, B, C, D. They're all lying on the circle, circumference of the circle. So this quadrilateral is a cyclic quadrilateral. Now here, what I did was, I extended this AB. See, this is one side AB of the cyclic quadrilateral. I'm extending it. So when I extend it, what happens is I get an exterior angle. I get an exterior angle of the cyclic quadrilateral. See this angle, which is CBE. This angle CBE. Now, the statement, the theorem says exterior angle of a cyclic quadrilateral is equal to interior opposite angle. Now, what will be the interior opposite angle to this exterior angle? The interior opposite to this exterior angle will be this one. It is this angle ADC. Remember, it is ADC. So angle CBE will be equal to angle ADC. Similarly, if I have, say, if I extend this one, I extend AC, I have, I'm sorry, BC, I have BC, let me extend it. So what happens? I get an exterior angle here. Yes, and this angle will be equal to interior opposite angle, which is this. So if I call this as F, so I can say angle DCF, I can say angle DCF, DCF is equal to angle BAD. I hope you followed this. So please write this statement also and draw the diagram. Write the statement and also draw the diagram. Do that. You will have to write this statement in your notebook and draw the diagram. See. Now the similar kind of idea we will derive from this diagram and this statement. See, similarly in the adjoining figure, look at this. As I said, angle PAB is equal to angle BCD. You can check where is angle PAB. PAB, say this, it is equal to BCD, this. You see this? Okay, interior opposite angle. This angle is interior adjacent angle. And here you got interior opposite angle. Then angle QBC, see QBC, needless to say, This will be equal to what? QBC will be equal to ADC. Check ADC. And then RCD, angle RCD. RCD. This one is RCD. This will be equal to what? Angle BAD. See? RCD. I hope you followed this. Okay, students, now we are in a position to solve few problems. Let us start solving few problems. We will take few problems now. So, hello students, see, this is a question from exercise 17A. This is first question. And this is definitely being the first question, very basic and very interesting question. Let's read the question. It says, in the given figure, O is the center of the circle. See, this point O is the center of the circle. Angle AOB, angle AOB, I'm sorry, angle OAB, I'm sorry. Angle OAB, that is this angle, OAB, and angle OCB, OCB are 30 degree and 40 degree respectively. It has been already shown in the diagram. See, 30 degree and 40 degree. Find angle AOC. We have to find this angle. See, this is the angle that we have to find, AOC. Okay. Show your steps of working. Now here I got an idea, students. See, how will I go for it? You know, I understand. Look at this angle AOC. Look at this angle. This idea you will develop slowly and slowly as you go ahead in the topic. This angle AOC is being subtended. It is being subtended by the arc AC. Look at this. It is this arc. It is this arc which is making angle AOC. Okay. Don't worry about the kind of diagram that I'm making. You know, this is I'm writing with the help of a pen tablet, and see, it is not that easy writing on a pen tablet. The way you write on notebook, you can't write it on pen tablet. The hands actually shake while writing. So here, see this particular arc AC is making, it is subtending angle AOC at the center. And the same arc AC is subtending angle ABC at the remaining part of the circle. See, if AC is the arc that we are considering, so what is this arc? This arc becomes the remaining part of the circle with respect to this arc. AC is the arc considered, so ABC is the remaining part of the circle. So AC makes angle AOC at the center, and AC makes angle ABC in the remaining part of the circle. So automatically what will happen? This angle AOC will be double of this angle. If this angle is X, then this angle AOC will be 2X. So what is my aim now? My aim is to find angle ABC. If I could find angle ABC, I will get angle AOC. Now see, how do I find angle ABC? For finding angle ABC, what I do is I join O with B. I join O with B. So I have to write all the steps. See, it is written showing your steps of working. We have to show the steps of working. So here what I write join O with B. I write here, my answer starts here. I write join points O and B, right? What is OB? OB is equal to OC. OB is equal to OC is equal to OA. They are all radius of the same circle. Yes, they are all equal. Why? Because they are all equal to radius of same circle. Okay, fine. Now see, if this is the case, now what? Look at the triangle OBC. Now in triangle OBC, can I say that OB is equal to OC? Yes. OB is equal to OC because They are the radius of the same circle. Now, if OBC, triangle OBC, OB is equal to OC, it means this triangle is an isosceles triangle. Okay. In triangle OBC, which is an isosceles triangle, triangle OB, therefore triangle OBC is an isosceles triangle. And if it is an isosceles triangle, what will happen? Angle OBC will also be equal to 40 degree. In an isosceles triangle, the angles opposite to equal sides are equal. You know that. See, this angle OBC is opposite to OC, and this OCB is opposite to OB. Okay, the angles which are opposite to equal sides, they are equal. So here I will have angle OBC. See, angle OBC is also 40 degree. The same thing, similarly, you know what? Similarly, we can write in triangle OAB. See, triangle OAB is also an isosceles triangle. Definitely, yes. It is also an isosceles triangle because in triangle OAB, look at this, OB is equal to OA. So what will happen now? If that is the case, this angle, the angles opposite to equal sides are equal. So this angle OAB being 30, here this angle will also be equal to 30. Therefore, I will write angle OBA is equal to 30 degree. Now see, I got this angle is 30 and this is 40. So angle ABC will be 30 degree plus 40 degree. See, this angle ABC. What will this be? This way is nothing but sum of these two angles. So I can write angle ABC is equal to angle OBA plus angle OBC, OBA plus OBC. That is equal to 30 degree plus. So this is 70 degree. Angle ABC is 70 degree. And I know that angle AOC is 2 times of angle ABC. I will write here angle AOC is equal to 2 times of angle ABC. So angle AOC is equal to 2 times 70, that is 140 degree. This is 140 degree. I hope you followed this. You can write the reason here. What will be the reason that you will write? You will write angle subtended by an arc at the center of a circle is double the angle subtended by same arc at the remaining part of the circle. You can copy this. Please go ahead and copy this. Do this now.